Hello, I'm back, ready to wrap up electrophilic aromatic substitution. We got two more reactions to go, and they're in the same family of reactions, carbon-carbon bond forming reactions, which means they are a big deal, so we'll take some time on it. They're the famous Friedel-Crafts name reaction, alkylation and acylation. So here are the faces behind the name. Yes, these are 1870s, so classic reaction that's been around a long time, still used widely, so hence it's in your textbook. We will find it very useful, and after that, after we do the electrophilic 5, we have more reactions relating to aromatic systems to do. So we'll try to put that all together. That's kind of the goal for the rest of this lecture. So let's jump into Friedel-Crafts. So you'll see, suppose you wanted to take a benzene ring, or even one that's already functionalized, which is more likely, like ethylbenzene, and add an R group to it. We didn't cover that yet, hence the Friedel-Crafts introduction. So we're going to do a Friedel-Crafts. This is an alkyl group, so it's going to be called alkylation. So you need this R group with a leaving group attached. It'll usually be chlorine, but bromine's possible as well. Getting ahead of myself there. Let's see. T-butyl. So I'll write TBuCl, which equals this whole thing. Right? So that would be the R group with the leaving group attached. And you'd have your matching Lewis acid. What I mean by that is Al, you better have the chlorine to go with that, Cl3. Now what would that really look like? Well, that depends on what was already attached. So since this is a alkyl chain, it's electron donating, means it's an ortho-para director. So that means we're going to expect these sites to be where the product occurs. So our real product would actually have, let's do some ortho and para. And yeah, I would guess that para would be major because we're installing a large, bulky T-butyl. Okay, so what does that look like mechanistically? The steps of the mechanism are essentially the same. We're just changing out how the electrophile looks by having the R group there. So just as usual, our Lewis acid functions as a Lewis acid. It accepts electrons from the chlorine. The chlorine just happens to have an R group attached instead of another chlorine, like it had in the chlorination mechanism. So it's otherwise identical. And so, at least for this step, so it should look familiar. We have the plus there, chloronium ion, a minus there. And then what we effectively did there was make the chlorine a better leaving group. We already know that it's a good leaving group for making a carbocation, but this really makes it even easier for it to happen. So we do form a carbocation, which we're all familiar with. There we go. Here's a carbocation. Got to watch out for those because they can rearrange, right? Plus you have, of course, your product, byproduct AlCl4 minus. Okay, so when you form carbocations, preferably we like to see secondary or tertiary. Primary with resonance is also very stable, but we won't normally see that variety in here because we have to have alkyl chains only. Okay, R equals alkyl only. So we'll most likely be hoping for secondary or tertiary for it to undergo that mechanism. If it doesn't, it's actually okay. It'll just do an SN2 style instead. So I'll show you an example of that soon. But the vast majority of the time, you're going to see that a carbocation will form in the mechanism. And when you have a carbocation, like I said, we have to remember the three things it can do. So remember, it can rearrange, and that's always what we evaluate first because it'll do that before it does anything else. It can be undergo a substitution reaction and capture a nucleophile. So substitution. How does that have a substitution? Well, something came off the carbon, the leaving group, and was replaced with a new group. Substitution. That's the nucleophile. What else do carbocations do? Way back from organic 1, elimination. And that forms a pi bond. If we did that, it would never attach to the benzene ring, so it's not going to do that in this case. And also notice the title of this section is Electrophilic Aromatic Substitution, not elimination, so we're not going to be doing elimination. We will do number 1 if it makes sense, and then number 2 for sure. So number one, if applicable. Always evaluate it first. It's worth doing some different types of examples just to see how that would look. So let's do a few of these together. Not enough for solid understanding. You got to go dive in the homework and do lots of drills on these to see all the different variations that can pop up. So for example, I'm going to start with an electron donating group already substitute on a benzene ring. That's already a variation right there, right? You might want to go practice one with more than one group, right? Okay, so methyl. So electron donating. Weakly, right? So it's ortho pair director. So we're going to expect the products to be there. Methyl's small enough that it's not doesn't provide sufficient steric hindrance to prefer para. So where's our R group? Our R group is ethyl. Can that make a carbocation? If it did, it would look like this. That's not very stable. So instead, because it's primary, right? So to avoid the primary carbocation issue, put a little side mechanism here, we're going to see that what happens is the chlorine's not going to leave until it has to. So we'll skip all the way to the part of the mechanism where it's already locked onto the aluminum, and we have that complex that we've made so many times. So the only difference here is instead of letting chlorine kick off and form that primary carbocation, instead we'll do what SN2s do, which is backside attack, and let's pick with that one maybe. I'm going to do red. Attack that carbon, that's where the bond's being made. Now the chlorine can leave because something else is coming in before you can ever form a carbocation. Nice, now we'll have the toluene that's ortho ethyl with also the para variety. Okay, so that was a really tiny R group. Let's see what happens when we have a bigger R group with some branching, because that will happen too, right? So let's see, to save some time, you can skip ahead to visualizing what it looks like when the leaving group leaves. Okay, what does that bromine look like when it's going to leave? So that's ultimately what's going to happen. We're going to have a secondary carbocation. Okay, good. We don't need to worry about trying to do a SN2 route. We can just let it leave, and it will happen. Assume it will happen. So here's what it's going to look like. Okay, secondary carbocation. Tertiary is better. Let's see if we have a chance for that. Well, what do you know? Whenever you have a carbocation, which we'll call carbon 1, you can always look at the neighboring carbons, carbon 2, and I'll call this one 2 prime. If either one of them have a methyl or ethyl, excuse me, a methyl or hydrogen that can shift, it will do so if it benefits it to make a better carbocation. So over here, there's methyls, but if the methyl shifts, we put the carbocation there, excuse me, if the hydrogen shifts, we put the carbocation there, it's primary, no good. We do have a methyl here. If we did a methyl shift, we'd convert this to a secondary carbocation over here, no good. However, we do have a hydrogen here. If we do a hydride shift, a 1,2 hydride shift, why is it hydride, not proton, hydrogen, by the way? If we do a hydride shift, we take the electrons with it. It's like moving an H- around. And then it moves over here. Then we will have this carbocation, 1,2 hydride shift. Notice how we now have a beautiful tertiary carbocation. So that's about happy as we can expect to be right now. It will do that. Now we can have a benzene attack the carbocation. Well, remember, we are starting with toluene, ortho para director, and we're adding kind of a big group. So I expect the major product, which is all we were asked to draw, to have it at the para position. So there's toluene, and then I have to attach it straight to the carbon with the carbocation. So I have that branching first, then I have that come down. Okay, there we go. Couple more to watch out for with Friedel-Crafts. Nitro and amino. So nitrobenzene. It's actually going to be short and sweet. No reaction. Why? This also doesn't work with other functional groups that are so deactivated. So it won't work with nitrile attached or carbonyls attached. Got to be careful. Okay, so strong or moderate EWGs will cause no reaction. Now amino has a different problem. We're going to call it no reaction. There's technically just a side reaction that's totally undesirable that dominates. So because amino is a base and this is a Lewis acid, it just spends all its time attacking this. And it's like, hey, that's not the point. We're supposed to get that bond made to carbon, but instead the nitrogen and aluminum are making a bond that's totally unnecessary. So we're not going to use that either. And so no reaction for those. Sometimes you'll see like a little red arrow to also indicate that's not going to work, just to emphasize that. So watch out, that's a limitation with Friedel-Crafts alkylation. So I'm going to summarize those limitations because you do need to watch out for them. They will come up. Friedel-Crafts reactions can never occur with, I'm going to put amino down here, and let's just say electron withdrawing groups. Avoid them. Okay, the only one technically that they work with are halogens. So if you're in a pickle, you really got to get the halogen on first. It's okay. Klein allows that. But I just try to keep it simple and just say let's avoid electron withdrawing groups. So I don't go in that territory. So nitro, carbonyl, all of those, and then electron donating groups are fine. You just can't have anything less reactive than benzene or like a chlorobenzene. Okay. So the technical one is strong or moderate electron withdrawing groups. Second limitation or benefit, depends on what you're looking for. They can undergo carbocation rearrangement. Usually that's actually a limitation. So in other words, if you wanted something branched put on there as it is, it might not look that way when it's done because of the rearrangement. And the third problem with Friedel-Crafts is that it can actually undergo something called overalkylation. Because that first step, if you think about it, is you're adding an alkyl group, right? Which activates the benzene ring. That's electron donating. So think about what's going on here. If you're just trying to do this, let's say we had that ethyl bromide and AlBr3, just because you can see it like that as well. We're just trying to make ethyl benzene. So let's say we do one equivalent of that. But of course, there's millions of these molecules in solution, right? Let's say we want to do just more than millions. I mean, that's but let's just simplify it. Let's say one benzene found one ethyl bromide. It reacted to make an ethyl benzene. Now this product, so suppose the whole flask isn't done reacting. This product's more reactive than the starting material. It's activated. That means that if this ethyl benzene dares to encounter some ethyl bromide that belonged to a poor unreacted benzene, it won't get it because this one's the faster one to react now. So what that means is you'll have this huge ugly distribution of products where you'll get some dialkylated, maybe even tri, but then you'll also get some benzene that never got to react because if you add it in a stoichiometric 1-to-1 ratio, some benzenes never got that ethyl bromide because the ethyl benzene stole it. So if there's no way around it, we'll still do it because there's always the chance to purify later. That's just a problem that is worth pointing out because you can kind of follow that with the logic we've learned so far. So it makes it even more nucleophilic by adding an activating group. So challenge for that. If you might have noticed that our other products so far have deactivated the ring. Like nitrobenzene is now less reactive than what it started with. So we've added deactivated groups. Friedel-Crafts is adding an activating group. So that's the one of the electrophilic 5 that makes it complicated. Okay. These limitations can be fixed in part if you need to avoid, especially number 2 and 3. Can't avoid number 1 with Friedel-Crafts. We can do the other Friedel-Crafts analog, the acylation. Notice the subtle difference? You have to have the carbonyl on there. It's not an alkyl group. It has to be an acyl group, which means a carbonyl with another R group. It doesn't have to be methyl. So let's take a look at what that looks like. Okay, so we are starting with phenol, which is activated, so electron rich. So it's an ortho-para-director, electron donating group, remember? So ortho-para-director, which means we think we'll get some product distribution right there, ortho or para. Let's draw our products. Start with phenol. Now, how are we going to add this? We add the R group without the leaving group attached. So this is the new connection point. So let's do the para first, plus, and let's just call this R. It doesn't have, it's just so we could generalize. It doesn't have to be methyl. And let's do ortho next. There we go. All right, let's form our electrophile. How does that look? It looks a little different, okay? So this first step is the same. You should be familiar with this first step by now. You might even want to skip ahead of me and do it yourself just to prove you can, because we're doing the same step with a different looking attachment. Okay, so this is electrophile formation. Chlorine attaches on to that aluminum. So the idea is we're trying to get that to be a good enough leaving group to get that R group freed from it. Chloronium ion, so this big complex. All right, now it leaves and it forms a carbocation, yes, but it's not your usual carbocation. So notice how we have an sp2 carbon here. And remember, when we form a carbocation, we go from an sp3 carbon to an sp2. The carbocation itself is usually sp2. So if it's an alkyl group, it's sp3. Then we make a carbocation, it's sp2. We likewise go down that level from sp2 to sp. So it's going to be linear. It's going to look like this, which is obvious because it only has 2 electron groups. And so it actually has resonance structure. So it's resonance stabilized, which is why, even though we don't usually like to form sp carbocations, the resonance structure kind of makes up for it, resonance stabilization. This is called the acylium ion. It's a famous carbocation that we see frequently. Still sp there. Okay, acylium. Know that name, it comes up. It's going to come up a lot in mass spec as well. Thing to know about it, why we focus on it, is that it won't rearrange, unlike the alkyl carbocations. So that's a benefit, right? So you could conceivably try to get a similar looking R group on that won't rearrange, but you'd have to still deal with that carbonyl. How do we react the substituents once they're on the benzene ring? Some of them will actually look familiar, like we've done reduction reactions before, and we're going to do a lot more. But this is a very interesting one. It's called the Clemmensen reduction. Once again, a name reaction. Clemmensen is the last name of Erik Clemmensen, a Danish chemist that was actually a pharmaceutical chemist that discovered this very useful reaction where it almost looks kind of crazy magical, where the carbonyl is just completely gone, but not completely because the carbon's there, right? So you're not losing the carbon, you're just losing the double bond oxygen. So complete deoxygenation using what's called a zinc mercury amalgam. It's like a mixture of the two. With HCl and heat. Now notice what happens. If the reason I cover it in this order is we just talked about Friedel-Crafts alkylation and acylation. So this looks like a product that would have come from an acylation, right? So from Friedel-Crafts acylation. That's where we'll see that in our big roadmap. We could take a product of Friedel-Crafts acylation, react it into so this is an acyl benzene, and we can react it into an alkyl benzene. Wait a minute, we've already made alkyl benzenes, and we did it with Friedel-Crafts alkylation. Why in the world do we want 2 steps to do one thing? There's a few reasons for that. Remember that Friedel-Crafts alkylation had limitations, and we can actually sidestep them, so a workaround, by doing an acylation first, then getting it reduced so we could do an alkylation. So I'm actually going to go back and actually label that those reducing conditions. Reduction. Okay, sometimes for reduction you see abbreviation H in brackets because it's thought of as a source of H. So notice there's 2 new H's here and the oxygen is gone. So you lose oxygen, you gain bonds to H. Okay, so why is Clemmensen so useful? Clemmensen's reaction is useful because we can convert an acyl group to an alkyl group, and it's actually kind of sneaky. So you can see that we're going to list those 3 reasons, and I'll give some examples. All right, so the reason that we want to do this is that we can force Friedel-Crafts acylation to do what alkylation can't do with certain alkyl groups. So you can have carbocation rearrangements. Oops, not possible. I keep going to that fat marker. Not possible. Or you can say avoided, because assuming those weren't desired. Okay, you can also avoid that overalkylation, because remember, when you add on an alkyl group, it makes it more electron rich. When you add on an acyl group, it makes it more electron poor. When you make it more electron poor, it's less reactive. But when you make it more electron rich with an alkyl group, it's more reactive. Stronger nucleophile, hence the overalkylation. So net alkylation without the overalkylation. And this is the sneakiest one that's kind of cool. It can be used as a meta director. What does that mean? Well, notice that if we arrive at this product from Friedel-Crafts acylation, this is a meta director, right? So we can direct right here and here and add some other business to it and then remove the oxygen if that's not what we wanted. But if we had started with an alkyl group, we'd be forced to go orthopara. So that's actually called a masking effect. It's like you're disguising the alkyl group. So when you want to use it as a meta director, and that's not when you actually wanted the alkyl group, we call that a masking effect. So therefore, can mask an alkyl group until you're done and ready. So let's do an example where we can use these strategies. Okay, so I always like to sprinkle some more examples in here for you to try. This is pretty straightforward, so I'll leave it for your homework. Feel free to check in with me. The moral of that one is it's not always going to give you a lot of problems, but let's do one where we might have to problem solve a little harder. So develop a strategy for synthesizing 1-chloro-3-ethylbenzene. So 1-chloro, so let's call that the 1 position. And if that's the 1 position, 1, 2, 3, that means that they're meta to each other from benzene. So we learned, okay, what about the order of putting reactants on, right? So let's see how this would go. Okay, this is an ethyl group. That's an orthopara director. So if we put that on first, we're going to get 1,4-ethylchlorobenzene. This is also an orthopara director. So what do we do? Well, if we only knew how to do Friedel-Crafts alkylation and chlorination, we would actually be pretty stuck right now. But here's our little friend here. Ooh, synthesis ninja. It's actually there for the mask. It's also a chemist. I thought that was a cute emoji to represent our masking strategy. So strategy. So we want meta. Oh, let's put her back. There we go. Problem. Our want meta, but only orthopara directors are present. So what happens is that if we have the proper masking ability, so she can come and actually mask that it's secretly actually a meta director in disguise. It used to be one anyway. So in other words, acyl chloride can mask what will be the alkyl chloride. So what do we mean by that? If we use Friedel-Crafts acylation, install the chlorine after that meta, Clemenson to remove the carbonyl was our mask, if you will, and then we're done. So she is basically the carbonyl that's going to come off. So the mask right here will come off with the Clemenson. Okay, so the carbonyl turns it into an electron withdrawing, but you want electron donating. So it's masking it that it will be a future electron donating group, which is an orthopair director. Let's put that into effect. So in other words, we need this order. We will put on the masked ethyl first. And so we get our Friedel-Crafts acylation all done. 2 carbons. Then we do our chlorination, Cl2, FeCl3. Notice this is a meta director. That's what we want. So it's going to go here or here. Mission accomplished, we can remove the mask. How do we do that? Clemenson reduction. So zinc, mercury amalgam, HCl. So this is the Clemenson to remove mask. And then we get the alkyl group we want. So that's a strategy commonly employed by chemists who has a workaround when there's a limitation. You can get creative like that. It's pretty cool. Okay, next reaction that we're going to do is to take one of our first ones that we covered, the nitration reaction, and see what we could do with it once we get a nitrobenzene. So it turns out that nitro is one of the most oxidized forms of nitrogen. NO2 has like one double bond to oxygen, so 2 there, and a single bond to oxygen, so it's 3 bonds to oxygen. That's very oxidized. We can reduce it all the way, which means remove all the bonds to oxygen and replace them with bonds to H. When we do that, we have an amine. When it's connected to a benzene, we call it an aniline group. We have 2 choices for that. We can use something that looks a lot like the Clemenson reduction condition, so not a surprise. But notice you see different metals in different books, the transition metals, iron, tin, you'll see zinc even, and then you'll say, well, wait a minute, zinc amalgam, will that reduce it? Yeah, so because it has zinc in it. So you can consider these very similar to the Clemenson reduction, but if you see iron or tin instead, that's usually specified for nitro. So it's kind of like a lot of those are tested in specific ratios to see what's the optimal reaction conditions, but they're both reducing agents. Okay, but also this is a familiar one, H2, palladium on carbon. This only works with nitros that are attached to a benzene ring, so we have 2 ways to get an aniline derivative. Now, once again, that's important to note that that could be a mask, right? Nitro can be an aniline mask. So notice that this is, nitro is electron withdrawing. Actually, I like to do those in blue usually, so let's do that again. I dropped my E on accident. Now we have electron donating, electron rich. Therefore, we could have nitro can be an aniline mask. So if you're trying to get something meta, right, to an amine, use the nitro first. Get the meta site on, reduce the nitro. More reactions to come. These are familiar ones, but they're worth pointing out again. When we have a benzene ring, we have another reactive site to worry about, the carbon adjacent, and that's called the benzyllic carbon. So that's right there. Why is it so reactive? Well, it actually is very easy to deprotonate. It's resonance stabilized. So if we keep that in mind, let's draw that out. So imagine, here's an H. These are called the benzyllic H's likewise. Benzyllic. So it's not an H, it's not an aryl H. Let's distinguish that. That's an aryl H. That's on the benzene ring. The benzyllic is on the benzylic carbon. That means adjacent, attached to the benzene, the carbon attached to the benzene ring, that H on that one. So aryl H, benzyllic H. Okay, so just get those terms straight so we don't grab the wrong one. So let's take a benzyllic H off. If we do that, we have a carbocation, and then it's resonance stabilized. So it's actually a very reactive site because it can delocalize throughout the ring, and we can draw several resonance structures. I won't draw them all. I'm just trying to get the point across that this explains why we see that reactivity, etc. Resonance stabilized. So we will see kind of a theme with these next set of reactions. Because the benzylic carbon's reactive, there are familiar reagents that we are going to use, i.e. they should have been covered in your Organic 1 class, but we are going to use them to target the benzylic site. If you don't remember, don't worry, because we're redoing them right now, but I'm going to go through them fast without doing every mechanism. So, and that's because it's already been covered as expected background. So you may want to go through the original chapters if you're struggling with how this works. So for example, NBS radicals, we did those Organic 1, and bromosuccinimide is what NBS stands for. That's a whole chapter on itself. So we don't have time to do duplicates of chapters. We're going to take advantage that we know that is radical bromination, especially when you see the photonolite. That's a hint because it doesn't use heat as its energy, it uses light. Bromination. Okay, so it will target the most stable radical, which is the benzylic carbon. So we get it there. We can actually keep going if we have more. And another way to say that is that we just add excess, right? And we could replace every benzylic hydrogen with bromine. It'll stop there. It's not going to take off any carbons. But if this was an H, and this was an H, and this was an H, and we had 3 H's, then it would be 3 bromines. That's as far as we'll go. Okay, so keep that in mind because that opens the door. We have an alkyl halide basically at the benzylic position. So that will generate new reactivity. Like we could do SN1, SN2, right? So this can open the door for substitution reactions and elimination. So you might see if you're planning a big synthesis, you're not going to be hindered by any of that inability to connect to substitution because you have a leaving group there. Another really interesting thing is we can have a mask again. This is an electron withdrawing group, but it used to be an electron donating group. Therefore, that can be a mask, right? So you can have, you don't remove it though, you have to kind of end with it. So this is an ortho-para director. This is a meta director. So therefore, you can have CBr3 ortho-para if you had the alkyl group on first. I'm trying to think of the right way to, it can mask an alkyl group, right? So watch out for a masking strategy there. It's just not a mask you can remove. You just block it and then it's stuck. So not supposed to, not as useful as Clemenson, where you can have it on there and then take it off and like it's almost like it wasn't there because there's that other secret reaction going on. But hey, this is, if you wanted, it affects the order of reaction, so it is significant. So if you wanted this meta, you'd install it first. If you wanted it ortho-para, then you do this. You wait to do the radical bromination until you get the other thing on, orthopara, then do this step. So it all comes clear with lots of practice, but it's more than just knowing the reaction, it's knowing how to use it in strategy. So watch out for that in your workshops. That's going to cover, we're going to be covering more of that. And I summarize that again on this page, actually. Last reaction. See, there's our masking ninja again. I'm going to summarize all the masking strategies in that box so you can be sure to take advantage of them. So that's what makes it fun, is when you kind of have your secret move under your belt, right? Okay. This is KMNO4, familiar reagent. You might also see some of the Jones type reagents like K2CR207 or Na2CR207. But what you should know is not let that trip you up. Like if you're looking at a different book, or sometimes the ACS exams you use different favorite resources, or some other study guide. Notice that oxidizing agent. We've been using these only as oxidizing agents, very strong oxidizing agents. How do we know it's an oxidizing agent? You see that ratio of oxygen to other elements in there? It's very high, right? It's pretty straightforward. So once you have a relatively high ratio of oxygen to the other elements present, then it's basically its job is to add oxygen. So it turns out that if you have a benzyllic H, in this case we have 3, and we're going to show where we have 2 benzyllic H's and only 1 benzyllic H. So I'm going to write that out here. Number H's. So they have to be benzyllic though. So 3, 2, 1, and 0. What's going to happen? We are going to get fully oxidized, replace bonds to H's with bonds to O. Instead of 3 H's, we have 3 bonds to O. Carboxylic acid. Okay. What if we only have 2 benzylic H's? Can we still make the carboxylic acid, or do we make a ketone? This is such a strong oxidizing agent that we actually do make that carboxylic acid. And say, wait a minute, we only have 1 carbon here. Wait, we had 2 carbons there. It cleaves any carbons after the benzylic position so that it can form that carboxylic acid. So that other carbon, carbon 2, comes off as CO2. That's the fullest extent of oxidation you could do on a carbon. So that one got oxidized as well, right? 4 bonds to oxygen. So I'm going to put the number 2 on there. We're tracking them. Okay, there's only 1 carbon there. So notice we have 1, 2, 3. What we're going to see is as long as we have a benzylic H, we are going to be able to be in business to make the carboxylic acid. We get the same product no matter what's attached, but this time we lost 2 carbons, so it's going to be 2 CO2. Only problem is if you don't have the benzylic H, it is going to have no reaction. You need the benzylic H directly attached. However, what is exciting about this, in spite of that limitation, is note what's happening overall. We're going from R to carbonyl. And remember that this is orthopara director, and the carbonyl, once again, we have our mask at play, is electron withdrawing, so it's meta director. So we can kind of use that to our advantage. If we see the carbonyl on there, we can say, well, when do we want to add that? When do we want to add the carboxylic acid? Do we want to do it right away or wait until we get something para first, or ortho? Okay, so these masking methods add a next level of kind of strategic difficulty to the synthetic problems, but that can actually make them more interesting and fun. We're not just doing a linear memorizing thing. In fact, avoid memorizing at all. You will accidentally memorize if you're practicing enough the reagents. That's really the only thing that you really want to call to mind pretty quickly, but that's bottom level understanding. That's not enough to ever really pass a test, let alone a class, with just knowing reagents. You've got to know what they do in all different scenarios, which means You have to problem solve through them. So, and that's the lowest level of understanding. Then you got to be able to apply different strategies to get different preferences. And masking helps with that. So, how do we use the mask as a synthetic strategy? Let's see. We've covered several masking approaches. So we could take something that was a meta-director and convert it to an ortho-para-director, and we could do the reverse, something that's an ortho-para-director, and let it be converted to a meta-director. And so I had these in a specific order, so I'm going to actually have a note for that. Just make sure I don't know if there's a reason I had them in a specific order. Yeah, it's okay. It didn't turn out to matter. But I'm going to give myself a little space up here. I'll zoom in on this one at a time. Okay, something that used to be a meta-director. Let's start with the order we covered it in, Friedel-Crafts. I wanted that to be black. There we go. Okay, so we have this scenario, very generic. This is a meta, once again, electron blue, meta-director. So it wants meta. So any future reactions on that would be meta. But it might be masking, if you so desire, if you're using this strategy, something that's actually a para-director. Now that's kind of squished there, so hopefully you can see that. But I'll circle it here. And what I'll do is I'll write that a little bit nicer. That's much better. So now we have a ortho para-director, right? The mask at play. There's another meta-director we've made that can be converted to an ortho para-director. So we have made nitro. Remember, that's a meta-director. But if that's not what you desire, then you can actually convert it to an aniline first. Only if that's what you wanted in the end, because we don't have we're not learning all the reagents to convert everything possible. So when you can go back and forth, it's extra valuable. But so what if we wanted to end on aniline? And we know aniline is an ortho para-director. It also has basic properties, but that's a different issue. So if we wanted to end on aniline and is ortho para-director, but we wanted it meta to something, that's when we would make sure that we didn't reduce the nitro till the very end. Okay, we also have the reverse available to us. We might have started with an ortho para-director like toluene, for example, in our group. Okay, and you can convert that. So as long as you have the benzyllic H there, we can convert that to something electron withdrawing, like NBS excess. That means more than one equivalent, as many as we need to react everything there. And everything there that reacts is all three of those benzylic H's to be replaced with 3 bromines, CBr3. So remember that we had an ortho para-director to start, and we got to finish with a meta-director. Okay, so let me get that one up here. Last one, ortho para-director to start. Which one did we do? Same thing, actually. Let's take toluene, our most recent one that we covered, and we add KMNO4. And there's often like heat or something like that added. Maybe a workup, like H3O plus at the end. That's not always shown, but it's part of the cleanup. 4, there we go. Okay, so remember that gives us our carboxylic acid. So that changes its directing ability. So we started with something that was ortho para. That would only occupy those sites with a subsequent reaction, but we can end on something that's a meta-director if we want. So you can use that strategy to your advantage, right? So do some practice, lots of practice, do all the assigned homework. Try this one too. This one will help you apply it. And we will check these together, I hope. That helps me know you're keeping up with it. So check in with me, see if you can do that one, and also do all the roadmap. So you can fill out the roadmap. It can be expanded now, right? We don't just have the Electrophilic 5, it's grown. So fill out the roadmap to occupy have all these new reactions in there, and then have that roadmap with you while you do the homework. It'll save you from like flipping through every note or scrolling through, however you have it on your study system. So it's a fun chapter, but it's a lot to cover. So don't hesitate to get a start on it. No procrastinating on this. I shouldn't say that because I'm a terrible procrastinator, but I hope that will help. All right, so have fun with your homework. Yes, homework, masking homework. All right, hope to see you soon. Bye-bye.